Hi everyone, thanks for coming. This session on the GP application in Astro and Cosmology. So I'm a PhD student in UC Riverside. So often my project involve using GPs, including classification and a GP emulator. And the co-host for this session will be Kier. Do you want to introduce yourself?
Yeah, hi everyone. I'm Keir. I'm a postdoc in University of Toronto, and I've used also Gaussian processes quite a lot in my research. So looking forward to the discussion.
Yeah, cool. So I guess we can start with a short introduction. What is a GP? So for me, GP is an extension of multivariate Gaussian distribution to infinite dimension. And what is a multivariate Gaussian distribution is an extension of 1D Gaussian distribution to multi-dimension. So for a GP, just like 1D Gaussian distribution, you can specify using the mean function and the covariance function. So how to design a GP always involve in what's your decision for the mean function and then the covariance functions. That's the quick summary from me. If anyone wants to add, please go ahead.
I think that's a good summary.
Okay, cool. Then we will go to what are the existing GP applications in the fields of astronomy and cosmology nowadays. So I list a list of should I share a slide, or all of you can see the slides, so I don't need to share. Anyway, I will share anyway. You see the slide?
Yes.
Cool. Is it too big or too wide? Something like that.
Too wide maybe, but we can read it. So yeah,
okay, cool.
Just move on.
So I've seen people using GPs for foreground removal, like a talk in this conference. Paula gave a talk about using GP to remove the foreground for the intensity mapping experiment. And then the second application I've seen a lot is the GP emulator, which is later on Benjamin, Sebastian, or Kier can add on this. And also the Bayesian optimization, likelihood-free inference, or expansion history reconstruction, and so on and so forth. There are lots of applications here. So I want to give over to the topic that's why we choose to use GP over others. So the first topic will be the GP emulators, and please Benjamin or Sebastian, you want to go ahead, please unmute yourself. Feel free to say something.
Oh, sorry. Yes. Yeah, I added this slide, didn't I? So this was one. Oh, yeah. So just as a general thing to say about Gaussian process emulators. Yeah, so they're useful for any statistic which you don't have an accurate analytical prediction for them. Sometimes you have an analytical prediction for them, but they're not that accurate. So you might want to instead measure that statistic from simulations, and then to generalize that statistic to other cosmologies, you can use an emulator. So yeah, I'm coming at this from the point of view of someone who regularly measures things from simulations and then wants to know how those things vary as a function of cosmology. And often those statistics are like statistics beyond the standard 2-point function. So in lensing, we have peak statistics, we have density split statistics. And on the left-hand side here, I'm just showing a plot from a paper that we brought out a couple of years ago that was to do with emulating the nonlinear matter power spectra in general extensions to lambda CDM. So yeah, and basically just what's being shown here is how accurately we could emulate those power spectra at different redshifts as a function of wave number, and these are like very non-linear scales. So this was just kind of one application that I thought I could highlight, but yeah, I'm really interested to hear about what other people use Gaussian processes for as well.
Yeah, Sebastian, do you want to add something about the Halo-based function emulator?
Well, I don't think I have much to add. I think Benjamin covered it pretty well. As he said, and it's been used a lot for extracting any kind, different kinds of statistics from simulations. I think one thing to add, which is part of what we're looking at here, is, I guess simulations is kind of an extreme example where, you could, instead of running a simulation that might take, weeks or months, you just basically interpolate the product over the cosmological parameter space. But also, I think on smaller scales, people are thinking of, replacing CAM with an emulator. So, the gain is not that dramatic, but in MCMC chains, as you all know, if you can go from, computing 10 seconds to like, 10 milliseconds, that's definitely interesting. Yeah, but anyway, other than that, I don't think I have anything to add. So thanks, Benjamin.
Okay, cool. Yeah, I do have a question. Like, how do people usually choose the kernel for the GPU emulator? Do you try different kernel in the first place and then choose the best one, or just go directly to the very smooth kernel?
That's a really good question, and I'm probably not the best person to answer it because I find myself just sticking with a specific kernel all of the time, the radial basis function kernel, or sometimes called the Gaussian kernel. And I find that there's so many different dials that you can turn with emulating a statistic in terms of like what transformation of the statistic do you emulate, and yeah, how, in what form, like all these things you can do to try and optimize the accuracy, that I never get so far as to actually changing the kernel and trying different ones. And I haven't really seen in the literature anybody using different kernels. That might be just because I've missed papers on that. But I always tend to see people using the same kernel. And I think it's a very theoretically kind of motivated kernel because it, you assume that statistics vary smoothly, and the closer they are to a simulation node, the closer that statistic will be to the one measured from the simulation. So it all kind of, makes sense. But yeah, I haven't seen people actually vary the kernel so much. So I'd be really interested to hear if other people have tried other kernels and what the effects were.
Yeah, I'm allowing myself to just jump in, basically just to second what was just said. Yeah, I mean, I don't think I can add much new here either. And I also think that for emulation purposes, indeed, it just seems to work. I mean, I know that in the Emulus thing, they have not used Gaussian kernels, but I think it was also just a kind of a prejudice that whatever they used would be better. But I think, as Benjamin just said, I think the underlying assumption, or the only way how these emulators can work is if the thing you're trying to interpolate is smooth enough. And I think I agree at that point, it just seems like the choice of kernel is not that important. So I think conversely, it's more was it part of the question saying like smoothness? And I think that's the important part. Like the function has to be smooth so that we can emulate it. And it seems that at that point, it doesn't matter too much. And at least my take on that was that, you know, some of the book examples and other examples, the function does really complicated things. I think there it, you know, intuitively makes sense that you could or should tune the kernel to what the function does. But, you know, in the emulation case, the function just basically grows. I don't know, like the halo mass function, the thing I did. I mean, just if you increase omega matter, the halo mass function increases. I mean, probably not in a straight line. That's why we have the Gaussian process, but it increases. So I'd be surprised if you need a very complicated, oscillating kernel, anything like that.
Yes, yes, thank you. That's also the things I heard a lot from people that it doesn't really matter because it's just smooth function we want to emulate.
I could add something, which is actually in our work, we tried a linear combination of kernels. So we had a linear kernel plus an RBF kernel. And the motivation for that was that linear interpolation had worked reasonably well before. And so it seemed reasonable to try the linear kernel. But by having it as a linear combination, it effectively acts as like an OR gate. And so you find that the optimization actually ends up preferring the RBF kernel anyway. It assigns much more variance to the RBF kernel relative to the linear kernel. And so that's basically telling you that what you've said before, that it just wants that RBF kernel because that has the most flexible properties. I have tried other kernels like rational quadratic, where you have that power factor. So effectively, it allows you to have multiple, like a sort of a spectrum of length scales. So it's an extra flexibility, which can sometimes be appropriate. And regarding like very specific kernels, like the periodic kernel, you could envisage of possible problems where you might want, if you knew there was some periodicity in your function, then perhaps that would be the kernel to use.
Yeah, thank you, Kier. So maybe we can go to next slide, which Kier will tackle it. Please go ahead, Kier.
Yeah, so I talked about this in my parallel talk, so I'll just go over it relatively briefly. The idea, so this is work for what's called a Bayesian optimized Gaussian process emulator. And this is tackling the problem of how to design the training set for the Gaussian process regressor. And in particular, it's considering the limit where we have a limited amount of training data in a high dimensional parameter space. And in cosmology, that's often the limit that we're in, where the simulations that we're trying to emulate are very computationally expensive, but we have lots of cosmological parameters and also lots of nuisance parameters that we need to marginalize. And so my assessment of the current state of cosmological emulators is that they are achieving certain accuracy requirements, but often in a fairly limited range of parameter space, or at least we'd like to make more efficient use of the simulations that we do run. And so the idea here is that instead you give up the hope of a sort of global accuracy threshold, and instead you say that you want to have very accurate emulation in regions of parameter space that are important, i.e. that the data prefer. So you want to have lots of simulations basically at the peak of your posterior distribution and away into the extent of the tails that you care about, but you don't want to have lots of simulations away in the highly excluded regions of parameter space. And so then you iteratively build up the training set, and at each stage, you add simulations balancing two things to get better accuracy in the emulator. So you tend to add simulations where the Gaussian process variance is high, but also you favor regions of high posterior probability. So you tend to do this thing where you're throwing them in at the peak of the posterior. And you can iterate this process until you have convergence in whatever you're trying to converge in. So, for example, posterior distributions. And so this ties really neatly to Gaussian processes, because Bayesian optimization and active learning in general relies on having global estimates of the error in your surrogate model. And so you can use the fact that it's a probabilistic interpolation to get those error estimates that perhaps other machine learning models wouldn't be able to give. Yeah, so this kind of illustrates that. So the thing we're emulating is the function, which is the top row there, and that's basically the power spectrum or the halo mass function. And you see the typical behavior that we know. And then we use that to estimate some likelihood or some posterior distribution, which is the next row down. And in particular, the idea is that you could propagate the error from the surrogate model, your emulator model of the power spectrum, into the likelihood. And so you get this sort of puffing up of the likelihood because of the extra error from the surrogate model. And then the idea is that we choose where to add the next simulation by defining an acquisition function, which is the bottom row there. And you see that peaks at those two places. So it peaks where the emulated error is high, where that red band at the top is wide, but it will also always peak where the likelihood or the posterior is high, so that you tend to zoom in on that region. And then you just keep adding simulations at the maximum of that acquisition, and you retrain the emulator at each iteration. Yeah, Sebastian.
Well, this is obviously really cool. Sorry for the stupid question, but with likelihood, are you talking about basically the cosmological data set you're actually trying to probe?
Yes. So yeah, in the full version of this, if you had already collected the data, then you would use the likelihood that you have.
Okay, then I guess I mean, this makes a lot of sense. I'm just wondering, so what's your take on how you would, so what's the strategy then? I mean, are you, so you're analyzing the data first time, and if you're limited by the emulator, then you can basically run new simulations, construct a better emulator, and reduce the errors because you're not limited by the emulator. Or basically you do that until you're not limited by basically the theory. Is that kind of the idea, or how would you do this? What's the iterative plan then?
So the idea would be that, so you start with some initial Latin hypercube type sampling. So I would envisage that groups would run those sort of initial suites of simulations a priori, and then you would want to, you could do some sort of pre-optimization. We have forecasts as to where the data will lie, and so that could already inform a kind of initial stage of optimization. But then possibly once you've collected the data, that's when you can, that's when you want to make sure you have your converge estimation of the posterior distributions. That's when you run your final set of optimization simulations.
Okay, yeah, I was, no, I mean, that's right. I was just for a second worried about stuff like blinding and so, but that doesn't really matter because you say you choose it wide enough that it encompasses what you hope you're going to find, and then you could refine. Okay. Yeah, thanks. No, it makes sense. Yeah. Thanks for your patience.
That's okay.
So Any questions for here? Then I will move on to my one application, which is slightly off topic since all of the people here are talking about GP emulator. So my application is more classification. So what we want is using Gaussian process to classify then lemma absorber is like kind of very dense hydrogen clouds in the universe, which shows a specific absorption feature in the quasar spectroscopy observation. So what we use Gaussian process is not to learn to classify the absorption feature. Other than that, we choose to use Gaussian process to train the background quasar absorption model, which means the quasar spectrum without absorption profile, and then we use that to build the Bayesian model selection pipeline, which means you based on the Gaussian process model, you learn from the quasar spectrum, which you have a mean function like the plot I show here, and the covariance functions that you learn from the data, which is super flexible covariance kernel that you have some assumption on the decomposition of the covariance that you can decompose into the eigenspectra of the quasar spectrum. So the kernel will be something like the kernel k equal to something m is the decomposition of eigenspectrum times n the transpose. So and then in this way, you just using the maximum likelihood optimization to find the best choice for the M matrix, which is the dimension reduction of the covariance of the quasar emission lines in the observing window. And then because we also add another kernel to take into account the lemma alpha absorption noise, which is modeled by just Apollo. So the benefit of it is that, so there's another model using neural network classifying the same object we want to classify. But the difficulty of the neural network is that they need to have a lot of absorption profiles to train on their filter to know that what the absorption profile look like. But for our model, we didn't train the absorption profile. We just inject the absorption profile from the atomic physics. So we don't need to train absorption profile. In that way, we kind of avoid the training data is not enough for very high current density system, which means that the training data might not be enough for rare objects in the universe. So for the neural network model, they need to kind of simulate those rare objects for their training data. But for our application, we don't need to simulate our training data. We just train directly on the data. That's a quick summary for what I did before. Yeah, you need to have the estimate of the redshift to use it. So yes, so right now we just directly take the redshift from STSS, but we also have another application that you just assume the redshift to be a random variable that you kind of marginalize the redshift. So you can see that you have this Gaussian process model in the rest frame. And then you can use this model to assume the redshift to be a random variable that you try to sample the different redshifts to see which redshift that give you the best likelihood. You can kind of use that to infer the redshift.
Could I ask a question? And
yes.
sorry, perhaps this was what you were explaining, but I was a little confused. So I don't know so much about Gaussian process classification. So yeah, I was wondering about the kernel that you choose in that instance, and if like when you're doing regression, at least, you know, the RBF kernel is an obvious one that lots of people use. Is there one for classification that is kind of an obvious one to use, or is that kind of the thing you're still figuring out? Perhaps that's what you said. Sorry, I didn't quite catch it.
Yeah, so the classification is based on the Bayesian model selection. And if I allowed, I can show what Bayesian model selection looks like. So basically, it's just based on the Bayes theorem that you have different model. For example, you have model from the Gaussian process you train on the spectrum without any absorption features, and you have model that's the Gaussian process model with one absorption feature, with two absorption features, with three absorption features. And then you can compute the likelihood for each model based on the Gaussian process likelihood. And then you have prior for each model, and you just put into the Bayes theorem and compute a final model posterior for a given model you are interested. That's how the classification works in our case. So basically, we just use the Gaussian process to serve as a likelihood function, which will give you a probability that how well Gaussian process can describe this spectrum. And you can kind of twist this Gaussian process to have one absorption profile, two absorption profile, and you use those Gaussian process with absorption profiles to calculate their likelihoods, and then you put into the Bayes theorems and compute a final model posterior for each model. And if the model with one absorption profile has higher model posterior probability, then you classify this one to be the spectrum with one absorption profile. That's how the classification works in our case. Did I answer your question?
I think so. I was just trying to remember from this equation where the kernel, or sometimes called the covariance function, enters again. Is it in that likelihood, or
yeah, you use because the Gaussian process is kind of probability distribution, right? So if you have mean and covariance, then you input some data into it, then you will get some likelihood. That's the value we use for classification.
Okay, yeah, cheers.
Yeah, just like the 1D Gaussian distribution, you can input some data and it will give you some probability back.
Cool. Yeah. Thanks.
Yeah.
Could I ask about your DLA model? So how many free parameters? Do you just have one free parameter, the column density?
You mean the DOA model? So the DOA model, so DOA is the absorption profile we want to classify. And so it has two parameters. So one is the current density, which means how dense this object is, like in the sky. And the other one is the redshift of the DOA, which means what's the position of the DOA on the spectrum.
I see. And
Yeah.
the other question I had was, so typically when one does Bayesian model comparison, there's this issue of like sensitivity to the priors. And so I was wondering how you decide to set those priors.
The prior becomes important when the likelihood is weak. For example, when the spectrum is very high, very low signal to noise ratio, then different model will give very similar likelihoods. Then the prior will be important. And right now we use a data-driven prior, which is derived from the previous data risk, but we guess there are probably some bias there. But it doesn't really matter for a very strong likelihood case, like high signal to noise ratio case. But yeah, for conservative prediction, probably restrict on the high signal to noise ratio spectrum would be better. Yeah.
Do you have a rough estimate of what that signal to noise ratio is, where that's?
I think generally signal to noise ratio larger than 2 is good enough.
Okay.
Yeah.
Interesting.
So maybe we can move to the general discussion. Unless someone wants to talk about the foreground removal using GPs.
I would be interested to, I don't know this, I missed the talk, I'm afraid. So if someone saw the talk and could summarize it, I guess I could watch the talk, thanks to the format of this conference.
Yeah, I don't think I'm qualified to talk about this. So yeah, let's move to the general discussion, and thanks, I think Kier or Benjamin put some talking points here.
That was me, yeah.
Yeah, Kier. So when to use GPs over other NL models, and how to decide, especially nowadays a lot of people use neural nets, and that's the question I frequently be asked, like why didn't you use neural net, something like that. I'm very curious about what are the thinking or thoughts from the audience. Kier, do you want to go ahead to lead the discussion?
Yeah, well, I put some bullet points there as like, what are the pros and cons of the different models? And I was kind of thinking of GPs in juxtaposition to neural networks in particular. So, I mean, you know, there's the issue of physical interpretability, Bayesian interpretation, by which I'm kind of driving at the fact that the Gaussian process is absolutely a sort of robust statistical model, whereas a neural network can be constructed in that way, but is not always used in that way. And then the issue of feature detection, where, you know, a neural network is really designed in a way to extract features. That's basically what it's doing in the hidden layers. Whereas the Gaussian process is not really doing that, right? It's a kind of smoothing function. It's doing a different thing. And so if there are interesting features, we tend to have to do a pre-processing step, like a PCA compression or something like that, to feed it into the Gaussian process. And then there's all the issues of computational efficiency, training time versus actual evaluation time of the output of the emulator, or whatever the model is. And then I just put one bullet there right at the end about, this came up during the discussion in my parallel session, if there's a connection between Gaussian processes and neural networks, and whether that could be exploited in some way. So if you have an infinitely wide Bayesian neural network, so where the weights and the biases in the neural network have probability distributions, and as that becomes infinitely wide, that essentially tends towards being a Gaussian process. And so could we, all the problems where we use Gaussian processes, is there potentially advantage in using very large Bayesian neural networks instead, or does the difficulty in constraining all these extra hyperparameters that you have in the network act against that? So that's just bullet points to start the discussion. So I'm interested to hear what other folks think.
Yeah, to start, maybe I can share some of my feelings. So I think the most convincing usage for GPs for me is the combining with the uncertainty quantification and then connect with the Bayesian optimization, because you need to have some sort of uncertainty quantification to build your acquisition function and to know what's the next training point you want, training location you want to go to, and GP give you a very simple way without very large training data to do it. You can have like just a handful of training samples and help you to build a basic GP and help you to iteratively build your training set. You don't need to have lots of samples to train the neural net to do that. That's one of the most convincing thing in my mind to use a GP. But of course, the drawback is that I don't think it's possible for GP, for example, for the emulator, I don't think it's possible to emulate directly on the particle or directly on the simulation product, like the particle things. Yeah, but neural net probably can do that.
So in the sort of the large training set limits, that might be when we turn to networks.
Yeah.
Is it worth throwing out the easy uncertainty quantification? Has anyone here tried sort of Bayesian neural networks or ensembles of networks?
I've only actually employed only employed convolutional neural networks, and in that case, the choice to use them was kind of obvious because it was for image analysis. And yeah, in that case, like I imagine what convolutional networks were built for. But yeah, I am interested in in what circumstances you use I can't remember what you call it now, but your standard neural network where it's just multiplications and additions of the input through the different layers, that type of neural network. Yeah, I'm interested when you would choose that over a Gaussian process, because I've seen people build those to emulate, for example, the matter power spectra, and I wondered why they did that instead of the Gaussian process. But yeah, maybe as you say, it's to do with data volume, maybe.
I think Alessio left, unfortunately, but so he had a flash talk on a neural network emulator. And I know that he was trying a Gaussian process emulator at one point because we chatted about it, and then he obviously switched to a neural network. So I would like to ask him why he decided to do that. I mean, one guess I could make is that the neural network evaluation is very fast. So, I think the balance is like, if you've got large training sets, the neural network gets, it takes a long time to train, but the evaluation is a lot quicker for the neural network than for the Gaussian process because it scales by this n cubed term because of the matrix inversion. And so if you want something that is going to be quicker than a Boltzmann code, then maybe that's, you know, when speed is really of the necessity, then maybe that's when you could turn to a neural network.
Can I ask on that point? I mean, that makes sense. I've only ever used rather small training sets. I mean, how large does it, I mean, at what point is execution speed a limitation, let's say, for emulator purposes? I mean, do you know?
It's a, you know, it scales by n cubes. So I think once you get to the point of thousands of training points,
Probably, yeah.
then it's taking tens of seconds to do each emulator evaluation. There's actually a nice paper where they did a sort of benchmarking of different methods for emulators. This was specifically for 21 centimeter power spectrum, but they basically found that they had a very large training set, like 90,000 training points, and they tried training a Gaussian process on that, and it took over a minute for each evaluation of the posterior. And they even tried, so they actually tried a sparse Gaussian process. So you don't invert the full matrix, but you invert some submatrix within it.
Yeah, okay, for these kind of numbers, yeah, that makes sense.
Yeah.
I mean, another thing I would, sorry, I missed the beginning of when you discussed this slide. And now I realize that physical interpretation is probably what I mean. That, yeah, I think the nice thing with using GPs is that, I mean, you can use it as a black box, but I mean, basically you can really look into it and understand a lot more than what we typically put in the papers. I mean, you can almost understand everything it does, right? So I think that's definitely good in terms of, yeah, and understanding, you know, if you think it does what you want it to do, and also, you know, maybe as a, I guess, well, as a reaction to a lot of criticism about, you know, emulators, at least for the Halo mass function, people are like, well, shouldn't you try and understand exactly the collapse model and everything that's going on? And we're like, well, for cosmology, honestly, no. But still, I think, you know, looking at what correlation lengths you get and so on, you can at least still understand which parameters are important and so on directly from what it does, instead of using the emulator to then, you know, do sensitivity tests and so on. So I thought that this is definitely helpful kind of as an intermediate thing. You can still understand a lot about what's going on physically. Yeah, but sorry, you probably brought all that up, so apologies.
No, I don't think we did discuss that before, and I strongly agree. Yeah, that, you know, it's, especially with something like an RBF kernel, you know, the correlation lengths, we have a physical intuition for that. To play sort of devil's advocate, could you envisage using neural networks, but because it does this sort of feature extraction layer by layer, could you go into the layers and, you know, understand the network by actually analyzing what's happening inside the network? I think there was a conference I went to a couple of years ago, and I saw someone talking about this. I think it's especially useful for like convolutional neural networks, where these convolutions are really picking out features in the images. Perhaps it could be extended to linear networks.
Yeah, I always have a doubt on the interpretation of the neural net, because it seems for me that they don't interpret the neural net beforehand, they interpret afterhand. Do you know what I mean? Like they look at something in the neural net and try to say something for it detects. But for Gaussian process, like you know beforehand what's the meaning of the length scale.
Yeah, you might end up with some sort of
But,
confirmation bias, right?
Yeah. But it does sound interesting that some people are using like convolutional neural net that look at the saliency map, did I pronounce correctly? Like to look at the map that which part of the image that detect the feature more strongly to see what is actually captured in the neural net. Yeah, but I'm not sure the interpretation for that is I mean you can say something about the saliency map, but whether or not it's your interpretation, right? I'm not quite sure. You can say something, some region detect something, but whether or not you detect what you learn is a ear or is a nose, I'm just not quite sure that's the correct
I mean,
interpretation.
we do have, I mean, there are images in astronomy and cosmology where you could imagine there are features.
Yeah.
I mean, even possibly in the quasar spectrum case, you know, a Voigt profile is a strong feature. I guess we have a very strong physical prior as to what a DLA looks like in a spectrum, but we do deal with feature detection in. So not just thinking about emulators, but more generally.
Yeah.
I saw a paper on it was evaluating different saliency recipes with the neural net, and I think there was 5 different recipes, and they were running them to see which features in the initial maps were most important for determining the predictions of the neural net. And then they tested it with their trained neural net and then a untrained neural net. And what was sort of interesting was a bunch of the methods gave the same saliency maps for the trained map and for the trained network and the untrained network, which meant that the saliency methods weren't figuring out what features the neural net had learned. They were basically just picking out things like the biggest peaks in the highest signal to noise things in the initial map. So they sort of concluded like 3 out of 5 of these weren't particularly useful for figuring out what a neural net has actually learned. So I sort of didn't have loads of confidence in it in those saliency methods after reading the paper. I'm sure there are some that do work well and help you figure out what's happening inside the black box.
Yeah, that's interesting.
So we still have 7 minutes. Do people have more comments on this slide, or should we want to move to the next?
I think we could move on.
Yep.
Yeah, the next slide, I actually don't know anything about it. So it's proposed by Matteo I think it's in Euclid emulator paper that the question is about, do sparse polynomial chaos expansion emulators have an edge on GP emulators, or it is just a matter of personal preference? And does anyone know what is sparse polynomial chaos expansion?
I could. I'm not involved in that project at all, but as I understand it, basically, you're sort of fitting a very high order, a sort of set of very high order polynomials as your model, but then you have some sort of sparse regularization so that you knock out most of the coefficients and so you end up only fitting a few of the coefficients. That's my summary of it, but I've not used the method myself. One
like
issue with it is that their uncertainty quantification, as I understand it, is basically just done by cross-validation. So there's no sort of principled estimate of the error in the way that a GP does.
And I think I know why Matteo is asking this question, because him and I worked on the result from that 2019 paper I showed before. We worked on that together. And one of the things we were testing at that time was, could we achieve the same accuracy as the Euclid emulator using Gaussian processes? And so we sort of did a repeat of their kind of analysis where we had the same number of simulations, and I think it's a W0 WA emulator, or it might have massive neutrinos in, I'm not sure, but yeah, we basically recreated their setup with the same number of simulations, where our simulations were just halo fit predictions, and we found we got to like only about 3% accuracy, and in the paper they get to like 1% on the same kind of scales. And there was, I can't remember all the details, there might have been some differences, some residual differences, but we more or less shrugged our shoulders and said maybe sparse polynomial chaos expansion's better, but we weren't sure. So I think that's why he's asking it, but yeah, I still don't know the answer to that question.
So for this one, do you still do the PCA before this extension, or just directly apply on the?
They do PCA, yeah. They're doing this on the PCA coefficients, on the eigenvalues of the PCA coefficients.
I see.
Yeah,
the jury is still out on.
The jury's out. I mean, like I said, I don't know the method in that much detail, but I'm not. Their uncertainty quantification is a bit unclear to me. So when you say that the 3%, 1% accuracy, was that in cross-validation tests?
It might have been with a trial set of simulations. So just making another Latin hypercube of trial cosmologies contained in the training set, and running it on that, possibly. I'd actually have to go back and look at that, because I'm aware the accuracy can really kind of depend on your the trial predictions you run at. For one ensemble of trial predictions, you might get 3%, the next might be 5%, the next might be 1%, or something like that. You know, we've seen that kind of variation in accuracies when evaluated in that way before. So but I don't think we did it by cross-validation, and I can't actually remember how they did it in the paper now. Maybe that was cross-validation as well. Anyway, sorry, go on.
Do you remember how many test simulations you did run?
In our training set, we had about 100. In our test set, I think it was of order hundreds, something like that. I think we might have had more in the trial set by a factor of 2 or something like that. Yeah.
But is it at the same cosmologies as the Euclid thing, or? Sorry, maybe you said it.
Yes, did we do that? Oh no, I'm not sure we did do it exactly at the same training cosmologies. And I think the reason for that is because we simply didn't have the file of their cosmologies, all 100 of them. So I think we just tried it with Latin hypercube with the same prior range. So yeah, I don't think it was a very thorough test, if I remember correctly.
Well, that's interesting nonetheless. But yeah, I think I agree, as you say, with the cross validation. There's quite a bit of variance in that. So yeah, interesting to know. I mean, 3 versus 1%. That's quite something.
Yeah. Did you publish this, Ben?
No, that was just a side test we did actually, but maybe that could have been something if we'd pursued it a bit more, which is a comparison might have been good. Yeah.
And like you say, it's coupled in with just reproducibility, right?
Yes.
Yeah.
And I downloaded the Euclid emulator because I wanted to do polynomial chaos expansion, but the emulator you download is not retrainable, if I remember correctly. You can just give it a cosmology and it will give you the prediction, but it wasn't what I needed for the analysis.
As a last thought, are there any sort of these tests, these competitions? So what's the approach now? Are different collaborations just building their own emulators, or is there going to be a combined effort?
Well, my take is that there's not there's not too much coordination yet. At least, I think my take is that it's still all pretty, it's still pretty early, and I think many people are still figuring out, how to do things and how they can improve things. But yeah, I'm wondering too, if when's the time where we should just say, okay, what's a set of simulations we'd want, and who can chip in, and what can we do? Because I mean, we should probably have 2 emulators for cross-checking, but it's not clear that we need 6. But I guess then as usual, we're all guilty of that, right? Like, we want to have our own thing and put our name and compare it to everyone else. So I guess we're all guilty of that.
Exactly. But like that is, you want more than one emulator. Like, Planck had 2 likelihoods, right. But you could pool training simulations, right? I mean, if these things are really so expensive to run, let's pool resources.
Yeah, but I think, that's where what actually you described becomes interesting. That I guess there's a balance. It's probably that's a great strategy to improve the prediction near where we think the correct cosmology is. But then I think where things become interesting is what parameter space do you actually want to cover, like W or W naught, WA, and so on. And then, what do you want to do? Because I think, as we all know, then the tricky part is how do you cover the limits, the boundaries, basically, because adding stuff becomes really expensive. Yeah. So, then I don't know. Typically, no one has run campaigns of simulations where you just basically simulate on a shell around what you think the correct cosmology is.
Yeah.
So there's probably quite a bit of duplication.
It should be, as data-driven as we can be, given the practicalities of running simulations and the fact that, we're probably never going to be in a situation where we collect the data first and run the simulations and do all the analysis afterwards. So, but hopefully we could convince people, or I hope that we can convince people to do some sort of hybrid thing where you are willing to keep some computational resources, like do that part of the analysis after the data, or at least you could envisage like using initial releases of data to slowly refine your emulator.
But another thing that just comes to my mind is I think there's also practical limitations in what kind of data products you actually have for your simulations and what you can rerun, which typically, or what you can re-extract, which typically is nothing. So I think that's another aspect where, this is probably the right group of people to talk to, like, probably would be worthwhile to, have some kind of community document on what we, would want simulation campaigns to actually store, because again, just speaking from my experience, for the Halo mass function, we have M200 critical masses, whereas the other two emulators that were available had M for a different mass. So then the comparability is close to zero, and it's really hard to actually do more because then you need to reread in the particle data, and yeah, you don't do that. So I think these are also things to be to be discussed in advance, and just be like, okay, these are the list of outputs that please like store these so we can combine things. And I haven't seen discussions where this is being done, but I think we should do it.
Yeah, that's very sensible. Yeah.
One thing I just thought I'd add is when it comes to lensing, at least I think we find it quite hard to make one emulator that we could all use, because we have to tailor our simulations so much to the survey specifications, so like the redshift distributions. And another thing we're getting onto now is a lot of our statistics are a bit biased by the actual survey footprint and the shape of it and the holes in it and the masks. So you have to build that into your simulations as well. So you end up with an emulator that is really very tailored to a specific survey. But of course, the thing you can use more generally is you can store the mass sheets from the simulation, and you can ray trace and make new simulations with different redshift distributions. But the core sort of computation, that's all common, and that's stored and doesn't need rerunning. But yeah, we haven't yet got to a place where we could build an emulator where redshift information is a variable in it that you could easily change. At least maybe that's something that could be done in the future with more simulations at your disposal.
Are there other parts? Is there more to a survey that makes it specific than, let's say, the redshift?
Other than, say, the redshifts and the galaxy in shape noise measured in each redshift bin, and then we're looking more at systematics now, and we tend to have different treatment of like baryons and intrinsic alignment. So we've just made some simulations that have those systematics in them, and so yeah, I mean, I think it's not impossible. I think it's just a bit difficult to make something that is kind of a one size fits all.
Because when it comes to emulators being survey or collaboration specific, to what extent, say I had a matter power spectrum emulator, to what extent is that all I need, say, to say I want to calculate shear correlation function? There are window functions. Okay, the more general way of phrasing this is what are the summary statistics that one emulates?
So yeah, I think if you've got a matter power spectrum emulator, then that could be, I think, fairly easily planted in a pipeline like Cosmology, where that does a lot of your conversions from 3D matter power spectra to projected, and that can easily kind of tailor your analysis to your survey. So that emulator, I think, should work quite well. I think it's more difficult when you're wanting to emulate a statistic where you don't know its relation to the matter power spectrum. So yeah, like some of the things we've been looking at, like the I was going to say clipped shear correlation functions is something I've looked at where we don't know at all the analytical prescription for those. But then things like the PDF of the projected density, I need to have a look at Cora Orleman's paper because I think she might have worked out some relation between that and matter power spectra. But yeah, in general, it's, you know, when you lack that analytical prescription, a matter power spectrum emulator might be difficult to use.
Mm.